Alright, in this activity we're going to do parameter regression, this time with two heaters. Here's an idea of, we could do this with some squared error for our regression. Another objective function we could use is the integral of absolute error. Here we're just taking the absolute value at each measurement point between the predicted value and the measured value for both heater 1 and heater 2. So we're using fmin_con and fmin search. Similar to before, we're going to clear all, close all, and then initialize our directory. We'll create a file name. This one we'll call toHeaterResponse, and then we will first try to read that. If we don't, and if we can't, and we get an error, then we'll go ahead and move on to this. Here we'll create arrays for T1, T2, our time, and our heaters, and we'll create some step changes in each of our heaters. You can see from second 10 to 4 minutes in, we'll go ahead and put heater 1 at 70. Afterward, heater 1 from 400 to 600 will be at 90, and then from 600 to 750 at 30. Heater 2, on the other hand, from 4 minutes to 8 minutes will be at 100%, and then starting at 10 minutes, and then going for another 200 seconds, it will be at 40. So we're just going to step around and try to anticipate what will happen. We'll then connect to the lab, start our timer, start our figure, and then, similar to before, just implement our step changes, ticking away. And then finally, lab.off, and then saving the CSV, as you can see right here. If there is any error, we'll catch it and just turn the lab off and clear the lab for convenience's sake. I actually already have this saved. So we'll go ahead, we'll run it, and we'll plot the results. So here we go. You can see these step changes. Heater 1 actually goes down to 0 right here. And heater 2 goes up to 100, down, and then to 30, or maybe 40 it looks like. So here we have this nice profile. Heater 1 was pushing 80, about 70 degrees at its hottest. We have some up and down action. As well, though, you can see right here, at 240, heater 2 hadn't turned on, but it was already plateauing, receiving the heat from heater 1 at a higher temperature. So let's go ahead now, and let's look at how we might be able to regress parameters. First, if we do an FOPDT, we have an FOPDT where we include the disturbance now. And if we use this FOPDT plot function, we'll be able to look at our functions. It's actually left the sliders pretty close. It looks pretty good. And we'll be able to regress. Actually, let's just go like this. I'm not going to look at all. I'm going to start doing things. So first, you can see that's horrible. I remember gain usually was about 0.6, I want to say. And that's a little bit high, it turns out. So we'll turn it down a bit. Let's make it a little bit bigger, that way we don't have that in the way. So the gain actually seems pretty decent, maybe 0.5 instead. 0.5 is a little bit low for my taste, so we're going to do 0.55. Next is the change because of the disturbance. Let's go ahead and set that to 2.2. You can see now, because of the disturbance, heat is going from 1 and to heater 2. So let's turn this up to 6. Now heater 2 is a little bit high, so maybe turn this down to 0.1. And this back down to 0.55. And that's decent. Let's now change our tau p. That's the process time constant. That's usually about 120. It looks about right, but now we need to turn up our heater, or our gain, I should say, a little bit lower. I'm liking that. And then theta p, we need some dead time in there. Probably about 10 to 20 seconds. Let's try 20. I can see right over here, that's a little bit long for my taste. Same here, so let's change it instead to like 15. It's trial and error, but we're seeing physically how these different parameters affect the system, which is really just the goal of this exercise, is to have some intuition, or build up some intuition, about how these parameters affect the system. Next, we're going to optimize our FOPDT. So we have a couple different equations. We're going to solve for Kp, Kd, tau p, and theta p. If you remember before, f min con is in the form of a times x, which is going to be our parameters here, is less than or equal to b. So, for example, Kp, negative Kp, is less than or equal to 0. So k is greater than 0 is what we're saying. Similarly, k is less than or equal to 2. And this is the process gain. And so that's how we have our constraints. Similarly, if we go on, Kd, the lower limit is 0, the upper limit is 1. Lower limit is 50, upper limit is 250 for our process time constant. And our dead time is between 0 and 30, we're saying. Then we'll use f min con, and we'll optimize it. And then finally, we use this sim process to simulate the outputs so we can graph them. So we're using this regressed FOPDT, and then we're graphing. Before we did this with a physics-based model, now we're doing this with the FOPDT, at least first. You can see, there we go. That wasn't that bad. So let's see, what are these errors? So the initial point was at a local minimum that satisfies the constraints. And that's because our initial guess was so good, we did our graphical FOPDT fits so well that we were actually at a local minimum when we satisfy the constraints. So as it was varying these parameters, it didn't find one that was much better, and so it said, I think this is at least a local minimum. And so I can live with that, to be honest. I don't love how low this gets right here, but I can live with that. So let's move on now. So hopefully that makes sense as far as the process of regressing the parameters. Really, the moral of the story here is to use f min con. There's two things we need to think about. We need to think about our constraints and get them in the form a times x, which is the parameter we're constraining, is less than or equal to b, and we need to create an objective function. Similar to the last time, our objective for our FOPDT is created down here, where first we have the derivative of the process, and that's in terms of the FOPDT equation. Then we have an FOPDT plot function, which is what we used to use those sliders. It takes the FOPDT parameters as inputs, and it simulates the steps. Similarly, we have a sim process. This takes the parameters as well, and then will output the predicted temperatures. And then finally, our objective FOPDT will take the parameters as well as the heater settings, and it will return the prediction and then do the sum squared error between the heaters. Now we're going to look at a physics-based model. Our physics-based model will take this heater function, though we're going to regress u, alpha 1, and alpha 2. So those are going to be part of this p right here. You can see that right there. U, p1 is p1, alpha 1 is p2, and alpha 2 is p3. Next, we take the other parameters and our temperature states, or at least our initial temperatures, and then we have the similar differential equations as before. We have the heat exchange between the two, and then the differential equation for heater 1, heater 2, and we put it all in a vector. Finally, we have our simulate, which goes through and it simulates each step depending on the previous step as the initial condition, each time step, I should clarify. And then our objective function, again, is the sum squared error between the two. Then we have dt model, which takes as inputs th1, th2, tc1, and tc2. This is where we have our heater. And so let's scroll back up and let's look at this. This optimized FOPDT fit, which we've done. Then we have testing the dual heater physics-based model with optimization. And finally, we're going to look at a second order physics-based model. The second order physics-based model takes into account both the temperature of the sensors and the temperature of the heater. There will be some delay between the heater heating up and the sensor heating up as well. Now that sensor is so small, it likely won't be much. That's how we have a second order relation. We have the relationship between the outside environment and the heaters, and then our second differential equation, which is between those heaters which are heating up and the sensors, which are TC1 and TC2. So first, let's look at our physics-based equation. Let's go ahead and optimize this. We're going to optimize three parameters, U, alpha 1, and alpha 2. We're going to go ahead and just do no linear constraints, and we're just going to do upper bounds and lower bounds using LB and UB. To do that, we can still use fmin_con. We just come over here, we give it the function as before, our parameter guesses, A and B, even though they're 0, our equality constraints, which are also just empty vectors, and then our lower bounds and upper bounds, and NL_con, which are nonlinear constraints, also empty. So our initial objective function is 26. We can see that fit. We're already using a pretty good fit. We have pretty good guesses. And then it turns out again, local minimum possible. Constraints are satisfied. Let's go ahead and look at our output. So we improved a bit from this first initial dashed line to our result that we have. What are our parameters? We didn't output them, so let's go to our workspace then. Regressed _ there we go. Let's just highlight it. So our regressed parameters, U is equal to 6.3. Our alpha 1 is equal to 0.009. And our alpha 2 is equal to 0.0038. That's in line with what we thought before, where we thought alpha 1 was equal to about 0.007 with the 1 heater example. Here with 2, it's a little bit different. And that's why we update this. We take into account what's actually occurring. Now let's take into account our second order system, where we have the time it takes for our sensors to heat up as well. It's second order because we have differential equations, and we have differential equations depending on those differential equations. You'll also notice that our time constant here has the form m times cp times delta x divided by k ace divided by ac as well. And then we have these two taus once we can simplify that. So tau is equal to the difference between the heater 1, the change in temperature of our sensor only depends, we're assuming, on the temperature of its heater and the temperature of itself, so the difference between the two. In essence, we're just assuming that there's convection and conduction, mainly conduction between the two. We'll go ahead and look at it. We're going to use some constraints where we have these inequality constraints. There we go, that's what I was looking for. For U, US, where that will be the transfer between, here we can see where we initialize that. US is going to be the heat transfer between the two heaters. We'll also have alpha 1, alpha 2, and tau, which is that lumped parameter term right here. So let's go ahead. We have, let's just look at the limits. So U is going to be between 1 and 20. US is going to be between 5 and 40 because they're so close. Our alpha 1 is between 1 and 0.03, 0.001 and 0.03, I should say. Similarly, our alpha 2, which has a slightly lower level since it's limited, is going to be between 0.001 and 0.02. And finally, our tau is going to be between 5 and 60. Similar process, we're going to have an initial objective function, optimize it, and then look at our final objective function, then output the parameters, and then we'll graph it as well. And hopefully this code's making sense. Hopefully we've done this enough times that you have a feel for what's going on. This is where we should be hitting stride, and you should be able to do much of this on your own and come to these videos for guidance. So it's doing the optimization now. Our initial objective is about 70,000, but that's over a long time. That's over 15 minutes for both heaters. Alright, so our final objective function is about 0.74 as well. We were doing pretty well with our initial regression. So our U is actually 5.15, so it did change them. US is equal to 8. Alpha 1 is 0.009, alpha 2 0.003, almost 0.004, and tau is equal to 32. And we're doing pretty good. I think the predicted gain is a little bit low as far as I would probably, if I were to continue to fine-tune this, make US a little bit higher so we have a little bit more heat transfer between heater 1 and heater 2. Let's move on, and that's it. There we go, that's 2 heaters. We scrolled down, so let's go to the top real quick and let's kind of review what we did in this one. The objective was to fit empirical and physics-based predictions to the data for our 2-heater model of the temperature control lab, and use an optimizer to adjust these parameters to achieve alignment with what is actually happening. Now what we'll do is we'll use the parameters that we actually know, and we'll control based on them. Now that we have a better understanding of how our system will perform, we can use tuning constants to a better degree, and we can also just anticipate what will happen within our system better. And we'll do that within the next video.